This meeting's being recorded. All right, here we go. Okay, so today we are going to look at gradient descent. Okay, so gradient descent is a method for optimization. Okay, we learned about coordinate descent in 102A, or at least if you took it with me. And in this class, we are going to cover gradient descent, which is another method for optimization. And so I'm going to show you. So right now, we've been using calculus. So far, we've been doing calculus to solve for minimums. Okay, and the way it's worked is we would have some kind of function. In our case, we've had the loss function, which is the mean squared error. But it doesn't matter. We would have some kind of function, and what we've been doing is we've been using calculus to find the derivative or the gradient of this function, and we would set that derivative or gradient equal to 0, and we would solve. Okay, and so that's what we did a couple lectures ago. We had the loss function, and we took partial derivatives and we set it equal to 0 and solved. And then later on, we took the derivative with respect to a vector. So we did it all in matrix and vector notation. We took the gradient with respect to the vector w, as in our coefficients vector. We set that equal to 0 and we solved for w. Okay, and so that's what we've been doing. But sometimes we'll be in a situation where, yeah, maybe you can find the derivative, maybe you can find the gradient, but setting it equal to 0 and solving might prove to be very challenging or difficult. Okay, so just because you can find out what the derivative or gradient is doesn't mean you can set it equal to 0 and solve. And so so in these situations, you might need to use a method like gradient descent to help you locate a local minimum. Okay, and so this is one method that we can use. All right, and so just a reminder is that when you're fitting a model, what you're trying to do is you're trying to find the parameter estimates that minimize the loss function. So you've got a loss function that says, you know, this is the difference between your predictions and the actual values. And we're trying to minimize that loss function, that we're trying to get our predictions and our actual values to be as close as possible. And when we do that, what we're doing is we're going to treat the data as fixed, and we're going to treat the so the observed data are, you know, our x and our t's, or x and our y's, are fixed values. And the only things that are left to vary are the coefficients, the things like the slope, the intercept, any other coefficients that might exist in your model. Those are left to vary, and you are trying to find the minimum, the values of those coefficients that minimize that loss function. Okay, and so in 102A we did coordinate descent, and in this class we're going to do gradient descent. Okay, so just to go back, the derivative represents kind of the slope of a tangent line, and the gradient is kind of a multidimensional analog to the derivative, except it's what the gradient represents. The gradient represents the direction of the greatest increase rate of it represents the direction of the greatest increase of the function. Okay, and the magnitude of the gradient is kind of the rate of increase there. And so the big idea with gradient descent is that you've got some kind of surface. Okay, so you can imagine a function where the input is 2 dimensions. Okay, you've got an x1 and you have an x2. Okay, so you've got kind of this this plane here, but then the value of the function that you're trying to minimize is some kind of three-dimensional surface, right? And you're trying to find so if you imagine some kind of paraboloid, like some kind of bowl here, you're trying to find the local minimum, the minimum of the surface. And but usually you're not going to start there. You're going to start off on, some side of the hill, okay, or some side of the bowl. And so at this part of the surface, let's say you start off at this location. What you're trying to do is you're trying to find, you find the gradient. The gradient's going to point in the direction of increase. And what you do is you take a step in the opposite direction. So if the gradient says, if you want to get a larger value, head in this direction, you're going to say, nope, I'm not going to head in that direction. I'm going to head in the opposite direction. That will be downhill, okay? So, imagine walking in some kind of valley, and you want to say, well, how do I get downhill? But you're only able to, look in a small radius around you. You have very limited vision. You look at which way is uphill, and if you say, well, this way is uphill, I'm going to move in the opposite direction. And if you keep moving in the opposite direction of uphill, that should help you reach the bottom, or the bottom of some kind of valley or local minimum there. So this is what the gradient descent algorithm looks like mathematically. It's very simple. It is only one line. This line right here, this is what the gradient descent algorithm looks like. You have some multidimensional function f, okay? F takes in a vector w, and it returns a scalar value. So you start off with, in our case, w is the slope and intercept, or intercept and slope. And when you plug that in, you get back a scalar value, the total sum of squared errors, or the mean squared error, okay? And what we want to do is iteratively, we want to say, well, if I start off at some arbitrary slope and intercept value, what should the next value be in my iterative algorithm? Okay, so you're going to start off at w at time n, and we want to know what should w be at w time n plus 1. Okay, and the answer to that is it's going to be, take your current value w at time n, and then subtract off minus gamma times the gradient. Okay, so this part, this is read as nabla. This is nabla f. Okay, nabla f of w is the gradient at w. Okay, it's the gradient at w time n. And this over here is gamma. This is a scaling factor. Sometimes we call it lambda. It's just a positive constant, okay? And it can be anywhere, greater than 0, okay? It can be 5, it can be 10, it could be 0.01, 0.1, and your choice of gamma is going to depend on the function itself. There's not a clear answer, okay? So gamma, we might call it also this learning rate. It's some kind of scaling factor. It just has to be positive. And so all it is the next iteration is your current iteration minus gamma times the gradient. All right, so let me just show you what this looks like for some arbitrary function. And I'm going to do this using partial derivatives. Later on, I will do it using vector gradients, okay? But remember, the gradient of a function is the vector of its partial derivatives. So here, I've got the function f is x1 squared minus 2x1 minus 0.5 x1 x2 plus 2.5 x2 squared. So this is the function that I've got. And I'm going to find the gradient of it, which is going to be the partial derivative of this with respect to x1. Okay, and so if I take the partial derivative of this with respect to x1, I get 2x1, x1 squared becomes 2x1, minus 2x1 becomes minus 2, and minus 0.5 x1 x2 becomes minus 0.5 x2 when I take the gradient of this, or partial derivative with respect to x1. This is a constant with respect to x1, so it zeroes out there. Okay. I do the same thing and I take the partial derivative with respect to x2, okay? This first term is a constant with respect to x1, so it zeroes out. This second term is a constant with respect to x1, or x2, so it zeroes out. This third term with respect to x2 is going to be negative 0.5 x1. And this last term with respect to x2 is 2.5 x2 squared. And the derivative with respect to x2 is going to be 5x2. Okay, so this is my gradient. My gradient is going to be the coordinate produced by this partial derivative and this partial derivative. Okay, so we've got two partial derivatives, and the gradient is going to be the vector that represents these two partial derivatives. All right, so let me just show you. So here's our contour plot representing this, this two-dimensional function. Here's our contour plot representing this two-dimensional function. And this is what it might look like in 3 dimensions. We've got some kind of surface here, okay? And what we want to do is we want to find this local minimum, or in this case, it's also the global minimum. We want to find the minimum of the function, which is right here, kind of in the middle of this circle. And so, so I'm going to start off at some arbitrary location, okay? -5, 4, all right? And what we want to do, so I'm going to start off at -5, 4, which is like up here in this corner. And I'm going to try to end up down here, right? So this is what it looks like, okay? The gradient at -5, 4 is the direction of steepest descent, okay? And it is a vector. It's a two-dimensional vector, which says that it's going to be -14, 22.5. And the way I got this was back here we found the gradient, which is the vector of its two partial derivatives, -2x1 minus 2 minus 0.5x2. That's the first component. And then the second component is minus 0.5x1 plus 5x2. And so I'm going to plug that in. I got 2x1 minus 2 minus 0.5x2. And I plug in -5 for x1 and 4 for x2. When I do that, 2 times -5 minus 2 minus 0.5 times 4 gives me -14. I do the same thing with the other component of that vector. I plug in -5 and 4 here, and when I compute that out, I get 22.5. So the partial derivative at -5, 4 is going to be -14, and the partial derivative at -5, 4 is 22.5. So I got my vector of partial derivatives, and that's equal to -14, 22.5. And so to apply gradient descent, I take my current value. I take my current value of this vector, which is x1, x2. Okay, -5, 4. This is where we currently are, and we're going to subtract off gamma times my gradient. Okay, I have chosen gamma to be 0.1. This is an arbitrary choice. Okay, it's an arbitrary choice. Gamma is 0.1. And so I'm going to take my gradient, which I calculated. My gradient is this vector, -14, 22.5. And I'm going to multiply that by gamma, gamma being 0.1. Okay, so 0.1 times -14, 22.5 is the vector 1.4, -2.25. So that's what I have right now. And I'm going to add my current value, -5, 4. I'm going to add this scaled gradient vector. And when I do that, -5 plus 1.4 gives me -3.6. And 4 plus -2.25 gives me 1.75. So this is going to be the coordinate at the next iteration. All right. So I start off at -5, 4, and I'm going to end up at -3.6, 1.75. Let me just skip ahead a couple slides, and this is where I start off. I start off at -5, 4. This is my starting location, and taking one step in the direction of the gradient takes me to -3.6, 1.75, which is right here. Okay, let me pause here And please let me know if you are following along. So give me a green check mark if you're following along. Give me a red X or ask a question if you have any questions as far as where any of these values are coming from or what this picture even represents. Okay, so so let me know. Let me also give you the answer to the first quiz question. So it's Wednesday, and question 1, the first quiz question is B as in boy. B as in boy is the answer to the first quiz question. Okay, so about two-thirds of you have given me green check marks. The other third of you, maybe, I don't know, maybe you're not paying attention, or maybe you're not following along. I don't know if there's any questions. And again, first quiz question, the answer is B as in boy. Are we doing okay? So what I've done is I've plugged in the coordinates -5, 4 to get my gradient, and I've used the gradient. I've scaled it by 0.1. I've added that on, and I get the next coordinate, -3.6, 1.75. And that starts off at -5, 4, and this is my next coordinate, 3.6, 1.75. Okay, these slides represent, show how I have coded this up in R, okay? And so here I'm using partial derivatives, and later on I'll show you how we can do it using vectors. But here's my function, okay? So the function itself is this x1 squared minus 2 times x1 minus 0.5 times x1 times x2 plus 2.5 times x2 squared, okay? And over here, I've got the gradient. The gradient consists of two components, the partial derivative with respect to x1 and the partial derivative with respect to x2. So I've got df dx1, and df dx1 is found by doing 2x1 minus 2 minus 0.5x2, and that's what I've written, 2 times x1 minus 2 minus 0.5 times x2. And df dx2 is found by doing -0.5x1 plus 5x2, and I get -0.5 times x1 plus 5 times x2. And I put those together into a single vector, and I guess the return is actually unnecessary, but that's what we return. We return the a vector with the two components there. Okay, and so if I start off at -5, 4, and I use a gamma of 0.1, okay, just plugging in this vector, -5, 4, into my gradient function. So I plug in -5, 4. It tells me that the gradient at that location is -14, 22.5, which is exactly what we found earlier up here, -14, 22.5. And then if I start off at -5, 4, and I subtract off gamma times this gradient, then it gives me -3.6, 1.75, which is exactly what we said up back here. Okay, so so I start off at -5, 4. I end up at -3.6, 1.75, and I've graphed that with this. Okay, start here and I end up here. All right, so the next iteration is going to start at this coordinate, -3.6, 1.75. That's going to be my starting location, -3.6, 1.75. I plug that in to get my gradient at that location. Using the function, R tells me that the gradient at that location is -10.075, 10.55. And I'm going to take the starting location of -3.6, 1.75, and then multiply my gradient times gamma, which is a scaling factor of 0.1. And so I'm going to take a step of basically -1.0075 and 1.055. So I basically roll my decimal point 1 over. And so my next coordinate, if I start off at -3.6, my next coordinate is going to be at -2.59. And if I start off at 1.75, my next location is going to be 0.695. So I start off at 3.6, negative 3.6, 1.75, and my next coordinate ends up over here, okay? So that's the second iteration. And so I can do a whole bunch of these iterations. I arbitrarily choose to do 20. This is normally you would have your gradient descent algorithm run until the difference between one iteration and the next iteration is less than some epsilon value, right? You choose some kind of epsilon value and you say, keep running until the difference is small enough that I'm going to ignore it, okay? But here I'm just doing 20 iterations just for illustration. And the way this is going to work is that I'm creating a matrix with 20 rows, and I'm going to, with each iteration, I'm going to take my x vector and I'm going to store it into row I in my locations matrix. Okay, so I take my x vector, I'm going to store it into row I of the locations matrix, and then in each iteration, I update my x vector. Okay, I just say, take your current x vector and subtract off gamma times the gradient at your location. And we update our x vector right there. Okay, and so I do this 20 times. And finally, I'm going to plot this. Okay, I'm going to plot this, and I use the arrows function. And so the arrows function starts off in row I and ends up, okay, so the arrows coordinate, you give it the xy or the x1, x2 coordinates of your start and the x1, x2 coordinates of your end. So I start off in locations row I, and I'm going to end up in locations row I plus 1. So if I start off in row 1, I'm going to end up in row 2, and I repeat this all the way through the entire matrix. And so I go through rows 1 through 19. So the last arrow that's going to be drawn is going to be going from row 19 to row 20. Okay, and so when I plot this, this is what it looks like. So I started off at negative 5, 4, and this was my first iteration. This is my next iteration, and here's my next iteration, and so on and so forth. And we can see as we go down, the difference gets smaller and smaller and smaller. My gradients get smaller as I approach the local minimum. The steepness of the thing gets less steep and more shallow, and therefore my gradients will actually get smaller. The size of the gradient is related to how steep the slopes are. And so as we get towards the minimum, it's going to become less steep, and so your gradients will get smaller, and therefore the steps that you take get smaller and smaller as well. So this is what it looks like. Okay, is that all right? How we feel about this? We're feeling okay. All right. Thanks. Thanks for your thumbs up there. Okay. So here, in all of these things, I just arbitrarily chose gamma to be 0.1. Okay. And so I just want to show you what happens when you choose different sized gammas. Okay. So if you choose gamma equal to 0.03, okay, then basically you're taking smaller steps down the hill. Okay. So here, I was taking, this was the size of my first step with gamma at 0.3. I'm moving in the same direction, but my step is only 30%. It's a much smaller step. And so I have to, so I keep taking more steps. And so what this means is that after 20 iterations, okay, I haven't progressed as far, okay, because I'm taking much smaller steps. So smaller steps are okay, but what often happens is you're going to need a lot more iterations for it to work. And so that's going to require more computational time, which, in some cases it doesn't matter. For a simple function like this, who cares? But in other cases, if you've got a huge function, each iteration can take a while, and anytime you can save computational power, then that's a good thing. So that's what happens when you take a gamma that's a little too small. let me just kind of show you here. If I increase my gamma to 0.15, I'm taking a bigger step. So here's kind of gamma at 0.1. This is what it looked like. Gamma at 0.03, I've taken much smaller steps. Gamma at 0.15, I'm taking much bigger steps, and this gets me down to the center a lot faster. Okay. But then there's also such a thing as taking a gamma that's too big. Okay, so here's gamma equal to 0.3, and now I'm taking steps that are a bit too big. Okay, so you can imagine, again, you've got some kind of valley. Okay, you've got some kind of valley surface, and you're starting off over here, and ideally is you're going to walk down the hill. Okay, each step you keep going down the hill. But in this case, my step was so big that I started over here, and the step I took was so big, I overshot the bottom, and I end up on the other side of the hill, okay, on the other side of the valley. I start over here, and I end up over here, okay? And then I take a step, and I end up back on this side of the valley, and then I end up back on this side of the valley. So that's what's happening. I start off over here, I take a step that's too big, I miss kind of the bottom, and I end up on the other side of the valley. And then I take a step, and I end up going past the middle, and I end up on the other side of the valley. And so I get this zigzag pattern, okay? But at least I'm heading towards the correct direction here. It's possible to take such a big step that not only you miss the bottom of the valley, but you end up on the other side of the valley in a steeper location, okay? So imagine you've got this valley, okay? And again, you start off over here, and the idea is you're going to walk downhill. But here you've taken such a big step that you've missed the bottom of the valley. You end up on the other side of the valley, and you actually end up higher on the other side of the valley. You end up in a steeper location on the other side of the valley. And if that happens, then you're going to say, oh, goodness, I've taken 2 steps. I need to go back in the other direction. And in the other direction, it's going to say, well, you need to take an even bigger step, because the size of your step is related to how steep your slope is. So you've ended up on the steeper side, and so you end up overshooting in the other direction, and you go way too far, and you overshoot in the other direction, and it just diverges all over the place. So what you choose for your gamma can have a profound impact on the performance of your gradient descent. Okay. And there's not we don't have a good way to say this is going to be the best gamma. Okay, right now gamma, your choice of your learning rate, your choice of gamma or lambda or whatever letter you want to call it, is a little bit arbitrary, and it's a lot of trial and error. Okay, so you start off with some value and you hope it works, and generally you start with something, and if it doesn't converge, you say, okay, well, let's try a smaller one. Okay, and you try going smaller. And then, and on the other hand, if you start off with a small value and it seems to converge, you say, okay, well, let's try something a little bit bigger. And you keep increasing it until it kind of breaks, because generally you want something, you want the biggest gamma that works, that doesn't break the algorithm in terms of break the convergence. So there's a lot of trial and error. You can read up different papers on how to pick a learning rate, but there isn't a great strategy. There's nothing where you can say, well, let's just look at the function, and based on what I see in the function, I know this is going to be the right gamma to use. That doesn't exist. All right, let me show you gradient descent using matrix notation for ordinary least squares regression. Okay, so in ordinary least squares regression, this is our loss function. Okay, and our predicted value f of xn is given by this matrix operation x times w. Okay, so this applies only to ordinary least squares regression, but our loss function is given by this. Our predicted value is matrix x times vector w. Okay, and I'm going to just start off with kind of simple linear regression, in that you've got just an intercept and a slope to predict. but this can be expanded to anything else as well in this linear regression form where the predicted value is x times w. Okay, I'm going to just skip over this part where we find it without using matrix notation. I'll let you figure this out, but this is the partial derivative of the loss function with respect to w0, the intercept, and this is the partial derivative with respect to w1. And we don't have to solve for where the partial derivative is equal to 0. We just need the partial derivatives or the gradient. In this case, with matrix notation, this is my loss function, and the gradient of the loss function with respect to w is given by this, okay? We did the same operations and we did these same steps a couple lectures ago, and when we did it in the lectures back, what we did was we set this gradient equal to 0 and we solved for w, and we said this is going to be the solution that minimizes the function. Okay, this time we're going to do gradient descent, so we don't need to set this equal to 0 and solve because we're going to assume we're in a situation. We're going to assume we're in a situation where setting it equal to 0 and solving is very hard. Okay, in this case it's not, but there's a lot of situations where you can find the gradient of a loss function, but solving for where the loss function is equal to 0 is very challenging. And so, so we're going to pretend we're in some kind of situation like that, and we are going to use gradient descent. We're not going to try to solve for where this function equals 0. So this is the gradient of the loss function, okay? And here it is. Again, the gradient descent algorithm in matrix notation is just take your current value of w and subtract off gamma times the gradient at w, okay? And that's how we update w. So when I code this up, this is what it's going to look like. These are my coordinates, okay? This is, I've got just a set of 3 data points, okay? 1, 3, 5, with outputs 4.8, 11.3, 17.2. And the true solution for ordinary least squares regression here is going to be an intercept of 1.8 and a slope of 3.1. That's the true solution here, okay? But but we're going to try to arrive at this using gradient descent, okay? And so this is the entire algorithm here, okay? I have a function to calculate the gradient, okay? And the input is the w vector, okay? So the w vector is a vector of length 2, and remember the gradient when we found it is negative 2 over n x transpose t plus 2 over n x transpose xw, okay? And when I decided to code this up in R, I got rid of the constants, okay? I'm just going to have it negative x transpose t and x transpose xw. I got rid of these constants 2 over n because that can get folded up in the gamma constant. So there's going to be a gamma constant that I can kind of wrap up in here. So this is what I have. I got negative x transpose times t plus x transpose times x times w. That's the gradient for some vector w, okay? So I'm going to start off with some vector w, arbitrary location. I'm going to start off with an intercept of -1 and a slope of 1.5, okay? That is very different from the true solution where the intercept should be 1.8 and the slope should be 3.1. So I just start off with w vector having an intercept of -1 and a slope of 1.5. I use gamma equal to 0.02, and I run 1,000 iterations of this, okay? 1,000 iterations, which is kind of a lot. And so I start off at -1, 1.5. I calculate the gradient using these matrix operations. Again, negative x transpose times t plus x transpose times x times w. And this is going to return a 2x1 matrix, and I tack that on, add that on to w vector, or subtract that from w vector, and I update w vector. And I do this 1,000 times, and after 1,000 iterations, it says your value of the W vector is 1.799995, which is very close to the true value of 1.8. And the slope is 3.100001, which is very close to the true value of 3.1. Okay, so after 1,000 iterations, we get something very close using gradient descent, very close to the true values here. All right, let's pause. Give me a green check mark if you're still following along. Or if you've got questions, raise your hand or put a question in the chat. Okay, again, is it considered a lot to do 1,000 iterations, or does it matter which starting point we choose? So is 1,000 iterations a lot? Not necessarily. Maybe. I guess it depends. The answer is as always, is it depends. If it's, in this case, each iteration is fairly quick. Each iteration only takes a couple matrix operations. So so I would say 1,000 iterations, not too bad. But yeah, I don't know. Okay, and that's using gamma 0.02, and you could try using a different gamma. Okay, doesn't matter. And in other cases, yeah, 1,000 iterations is not a lot at all, and you might do something like, you'll have what they call epochs of like 10,000 iterations or even more. And sometimes the training sessions using gradient descent will take hours and hours and hours. Okay, that's a reasonable thing. Okay, doesn't matter which starting point we choose. Yes, it matters. In this case, for ordinary least squares regression, it's just a simple bowl, right? The shape of the loss function is a paraboloid, right? There's one location, which is the slope and intercept that minimizes the function, and there's only one slope and intercept that minimize the function, and you don't have these weird local mins and local maxes. But if you had a different surface, okay, a different surface where there's different local mins and local maxes and stuff like that, one particular starting location can end up and have you end up in this local min, and a different starting location can have you end up in a different local min. And those are all different issues. And so, so one strategy is to try like multiple arbitrary starting locations and see if they all end up in the same location. If they all end up at the same spot, that's got to be the local min, right? So it's kind of like setting a bowling ball on a hill and letting it roll and see where it ends up at the bottom. And if your valley is shaped like a bowl, you know, you could start a bowling ball over here and a bowling ball over here, and they're all going to both end up at the bottom. Okay, but if you've got a different shaped hill or a different shaped thing with different surfaces, depending on your starting location, the local min could end up being different. And so, you know, gradient descent, it's great and it's very useful because it's very simple and easy to implement, but it's not perfect, and it certainly runs into problems. Okay, this is just some code to get the graphs going. Okay. But this plot represents the loss function. Okay, this plot represents the loss function for ordinary least squares regression. Okay, so for ordinary least squares regression, for the current data that we have, our 3 points, the loss function is minimized when the intercept is 1.8 and the slope is 3.1, and that's going to be this location right here. And this red path shows the path that gradient descent took. I started off with an intercept of -1 and a slope of 1.5. And that is very different from the optimal values. And so gradient descent took, this is the path it took. It went up this way, and then it came over here and it rolled down this way, okay? And so let me just show you what this looks like. So my starting location, I had an intercept of -1 and a slope of 1.5. That's given by this red line shows an intercept of -1 and a slope of 1.5, okay? And this is the data that I'm trying to fit, okay? And we can see that this red line does a terrible job of fitting the data. I've got 3 points, and I want to find the line that best fits these 3 points, and we can see this line does a terrible job. And so therefore, when we calculate the loss function, the loss function of the squared errors here is huge, okay? Between my predicted and my actual value, there's a huge loss there. Between predicted and actual, there's a huge loss. So the loss function, I'm very high up on the sides of my kind of paraboloid, my valley here. And so at the next iteration, gradient descent says, you know what you got to do is, your slope is 1.5. What you got to do is you got to bump up your slope. Your slope needs to get steeper. So it says try out a slope of 2.3. So that makes my line steeper. And it also says try a different intercept. Try an intercept of negative 0.77. So increase your intercept, increase the slope, and this is what we get. So this is where I started, and at the second iteration, I've made my line steeper, and we can see this does a better job of fitting the data. Okay, so we're going to start. We started off here. This is the second iteration. It does a better job. Okay, but it's still, we would say this is a bad line. This line does not fit the data very well. Okay, after a few more iterations, this is where we are. It says the slope is a lot steeper at 3.33, okay? And I've got an intercept of negative 0.459, okay? So I've changed my intercept. It's no longer -1, but now it's negative 0.45, and my slope used to be 1.5. It's a lot steeper now at 3.33, okay? And this is doing a better job, but it's not perfect. And so after several more iterations, this is where we go, okay? And finally, we're at a situation where the line is above a data point over here and below a data point here. And so here, the slope is 3.6, and the intercept is negative 0.23. So we're doing a better job, but this, again, it's not quite perfect. So this is the loss function is not quite the best line. And so what we want to do is we need to kind of tweak this thing, okay? So imagine you've got these two knobs, right? Like imagine some kind of like Etch-a-Sketch, except one knob controls how steep the slope is, and then the other knob controls where your intercept is. So one brings your intercept up and down, and then the other knob controls how steep it is. And what we're trying to do is we're trying to move the how steep or the intercept, just so that the squared errors get minimized, okay? And so so after some more iterations, this is what we get, okay? And we can see, okay, well that's pretty good. We're getting a slope of 3.4 and an intercept of 0.62. And after several more iterations, I get a slope of 3.18 and an intercept of 1.475. And it's going to take probably like 1,000 iterations to finally get to this central location. Okay, so as you approach the optimal, you're taking even smaller steps. So it takes a lot of iterations to get to the end. But this is what we have. Are these diagrams okay? Give me a green check mark again if these diagrams are okay. Or maybe I forgot to. Okay, let it. Wait. Hold on. Let me clear you guys out. Okay. Now go ahead and give me your green check marks if these diagrams are okay as far as what's happening, okay? So we're adjusting the slope and we're adjusting the intercept, and we're trying to get the line to fit the data as well as we can. And when we do that, our location on the loss function changes, okay? And we want to get as minimum as possible. And again, your choice of gamma matters. And so here I've chosen a gamma that's a little bit too big, and so we get this zigzag pattern, and that's that's a little bit of a problem here, okay? And but at least it gets us kind of towards convergence here. Oh, did you have a question? Or did you accidentally unmute yourself? Okay. Here, gamma is too big and we diverge. Okay, so that's, you don't want that. And again, you don't know. It's hard to know what gamma you should use. So you try things and it's a lot of trial and error. Okay. All right. The last bit I need to cover is estimating the gradient numerically. Okay. And so we've been using some vector calculus or partial derivatives to figure out what our gradients are. Okay. And but sometimes figuring out the gradient using calculus is hard, and you're not sure if you did it correctly. Okay, and that's one of the hardest things in statistics or whatever, is that you do some math and then you're just like, did I do my math correctly? Okay, and so what you can do is you can check your gradient numerically. Okay, this is not an efficient way, and you shouldn't do this in production, but before you implement some kind of algorithm, you should definitely do a numeric gradient check. All right, and a numeric gradient check kind of uses your definition of the derivative or the definition of the gradient, where you are going to just add on a tiny little value and see how much the function changed. So I did this in 102A, where we did a numeric derivative by adding on a tiny value like 10 to the negative 5, and we saw how much the value of the function changed, and that gives us an estimate of the derivative. We're going to do the same thing with the gradient. Okay, except as far as a gradient goes, when you add on your little constant, you do it one component at a time. So in our case, I've got a function of two variables, x1 and x2, and for the first component, I'm going to add on my constant h only to x1. Okay, I leave x2 unchanged, and I add on h only to x1. And as far as the second component of the gradient, okay, I add on h only to x2, and I leave x1 unchanged. Okay, so that's an important thing. And what we do is you say, well, how much did the function change when I added on a component over here, and how much did the function change when I added on the component over here? And we do that. Okay, and so first, so I'm going to use kind of the same function that we used earlier back on, I think, slide 10, and I say, well, let's find out the value of this function at the coordinate -5, 4. Okay, the value of the function at that coordinate is 85. And what I'm going to do now is I'm going to add on a small value. Okay, in this case, I'm going to add on 0.01, which is unusually large, but just for illustration, I'm going to add on 0.01 to the x1 component. All right, and then I'm also going to add on 0.01 to the x2 component. But I do this one at a time. So first I leave x2, which is 4, I leave that unchanged, and I add on 0.01 to the x1 component, -5. So I leave the other value unchanged. So I'm going to see what is the value of the function when I use the coordinate -4.99, 4. Okay. At -5, 4, we found it to be 85. When I'm using 4.99, 4, my value changes to 84.86. Okay, so it goes down from 85 to 84.86, and that was just by adding in a 0.01. So therefore, my gradient at this location, it changed, is going to be -13.99. On the other side, if I add on 0.01 to 4, that takes me to 4.01. I calculate the function at -5, 4.01, and that gives me the value 85.225. Okay, so it goes from 85 to 85.225. Okay, and that was just by adding 0.01. So therefore, my gradient at that location is 22.525. So my numeric gradient is estimated to be -13.99, 22.525. And that's pretty close to the analytic gradient that I got back on slide 10, which was -14, 22.5. So this is one way for us to check our analytic work to just see if it makes sense computationally. So computationally, we would kind of estimate the gradient by tacking on a small constant. and this is what we get. Okay, and so we get these two things being quite similar, and that's a good sign. Okay, we will stop here for today, and I will see you guys on Friday. Good luck as you guys do your homework. I hope the homework's going well. Stay safe and stay healthy out there. Oh yes, second quiz question. Second quiz question, the answer is C. C as in cat. C as in cat for the second quiz question. Thank you for that reminder. So, okay, so we'll see you guys on Friday. Have a great day. And let me stop the recording.